Hello. In this video, we're going to be looking at trig form for complex numbers and the complex plane. So this is a really sort of interesting concept. We can actually plot these complex numbers on the complex plane. So this is how we do it. Let's say we have a number that looks maybe like this. So we'll start with something like z is equal to -2 minus 3i. So we want to plot this number, but we can't with our real number system. So the complex plane allows us to do this because we have these two axes being our real and imaginary axis. We have our x-axis being the real part of z, and our y-axis is going to be the imaginary part of z. So it turns out we can plot these a lot like vectors that we've been plotting or ordered pairs. So if I'm looking at this z is equal to -2 minus 3i, the real part of z is going to be -2, and the imaginary part without the I is going to be -3. So to plot this, all I do is I'm going to go -2 on the real axis. So I'm going to go over here on the real axis and then down 3 on the imaginary axis. And this is my point. So this point here would specify z is equal to -2 minus 3i. You might find that all the real numbers will actually be on the real axis, and all the imaginary numbers without a real part will be on the imaginary axis. So we'll sort of check this out as we go through the section. When looking at these numbers in the complex plane, we have some definitions that we can use just like vectors. So the absolute value or modulus of a complex number actually tells us the distance away from the origin to that point. We can use the Pythagorean theorem to figure that out. So the distance is denoted by r, and r is called the modulus. It is going to be, so the modulus or distance of a complex number is going to be essentially the square root of the real part squared plus the imaginary part squared. So you square those and take their square roots, just like the Pythagorean theorem. The argument of a complex number is essentially like the direction for a vector. So if we're given a complex number, we denote that angle, the argument, as arg z, and it's the smallest positive angle theta from the positive x-axis to the graph of z. So we're going to illustrate this by an example as we go along. And we're going to use these to write our numbers in trigonometric form. Now, trigonometric form or trig form is going to be a really useful way for us to manipulate these complex numbers pretty easily. So if we can find that modulus and that angle, that argument of our number in the complex plane, then we can find the trigonometric form of this number. So let's look at an example here as to how we would do this. So it says, graph the number 4 minus 4i and the complex plane along with its opposite and conjugate, then convert and write the numbers in trig form. Any relationships? Let's check it out. So if I was going to write this first number in trig form, first I would plot it though. Always want to plot these first. Let me go ahead and scoot this down a little bit. There we go. Okay. So I'm going to go 4 in the real direction and -4 in the y direction. My point for z is going to be right about there. So that's going to be 4 minus 4i. If I wanted to plot the conjugate, remember the conjugate is just the same number with the opposite imaginary part. So that's going to be 4 plus 4i. That's going to be in our first quadrant. So I'll go over 4 to the right and up 4, and I have z bar equaling 4 plus 4i. So that's the conjugate. And the opposite of that number is just going to be the negative of it. So that's going to change the 4 to a negative 4, and then the negative 4i to a positive 4i. So that should be in our second quadrant there. So negative 4 plus 4i, that would be the negative z. Okay. And see how we would find these numbers in trig form. What I'm going to do is I'm going to sort of make a triangle here. So I'm going to go over 4 and down 4. This will be really familiar. And I can actually draw something that looks like a vector to the point there. So I know that this triangle is going to have 4 and negative 4 for the sides. So my modulus is going to be that r there. You might see that this is a special triangle, but when we first start out, we'll go ahead and use the formula. So I'm plugging in that formula above. I have negative 4 squared plus 4 squared in either order. That's going to give me 16 plus 16, or the square root of 32. But the square root of 32 is 16 times 2. So the square root of 16 is 4, and that's 4 root 2. All right, I could also find that angle, theta here, that reference angle, so I'll just call it theta hat. I could find it using inverse tangent, but we might see that this is actually a 45, 45, 90 degree triangle, because we have a 4 to 4 to 4 root 2. So that theta hat is going to be 45 degrees. And if we want to put that in quadrant 4 for this number, we can write this z as the same thing as 4 times the cosine. That'll be 315 with a reference angle of 45 in the fourth quadrant, plus I sine 315. These are in degrees. Okay. Now we can look at the one in the second quadrant. So we're going to be looking at the opposite. This time we can use special triangles. We know that this is negative 4 and 4. So that's a 45, 45, 90 triangle. The modulus will be 4 root 2. And since this angle is 45 degrees, to get around to that side there, we're in quadrant 2 with a reference angle of 45 degrees. So we know this will be 135 degrees. So negative z would be represented by this vector. So we'd have in trig form 4 root 2. I'm going to use this shorthand form cis of 135, but just remember that the cis means cosine of 135 plus I sine 135, just like our one over here. Finally, to look at the conjugate, I'm going to go over 4 and up 4. And again, I realize that that modulus is going to be 4 root 2, and the reference angle is 45 degrees. So if I wanted to list this conjugate in terms of trig form, I would have 4 root 2 cis of 45 degrees, or 4 root 2 cosine of 45 plus I sine 45 degrees, all in parentheses there. Those are the same thing. And while I'm at it, I need to put in that square root of 2 down for the first one I had there. I made a mistake there. So are there any relationships here? Well, we might notice that they all have the same moduli. So all of them will be a length of 4 root 2 away from the origin. That sort of tells us that their distance of these complex numbers, if you want to think of those, is all the same. So we don't have ordering like we do with real numbers. Also, you can see that when you plot a number and its conjugate, you're really just flipping it about that x-axis. That's the real axis. That makes sense because the real parts are going to stay the same, but the imaginary parts are going to be opposite. Finally, if you're looking for a relationship between a number and its opposite, that's going to be the number that, just like that vector or number, flipped about the origin. So we're going to flip it right through the origin and we'll get the same thing. All right, hopefully this gives you a taste here. I'm going to pause and we'll look at some more. In this part, we're going to convert our numbers from trig form back into a standard form, and we're going to go ahead and plot these. So the first thing we're going to do is sketch them as they are in trig form. So what we want to do is we want to think about that modulus of 4, but this is spinning 30 degrees from the positive real axis. So if I'm plotting this, I'm going to be going out a distance of 4, but I'm going to be at an angle of 30 degrees. So it'll be something like this, where I have 30 degrees for my angle from the positive real axis, and my length is going to be 4. So that's what my point would look like. Let's see how close I got converting this over back into regular standard form. So all I have to do is compute the cosine and the sine. The cosine of 30 degrees is going to be root 3 over 2. And then the sine of 30 degrees, so I can sort of erase that there. Whoops. Let's see if I can just erase part of it. I don't think I can. Let me try again. So the sine of it, you have 4 times square root of 3 over 2 plus I, and the sine of 30 is 1/2. So when I convert this back to standard form, I have the 4 and the 2 canceling, so I have 2 root 3 plus 2's cancel, so 2i. So I'm going to use my calculator over here just to see how close I was. I know I erased that, but 2 root 3 is about 3.46. I think I was over about 3.46. I was somewhere in there. And then, of course, up 2. So if I go over 3.46 and up 2, that should be about where my number is. So Z1 should have been about there. But remember, to plot it with the trig form, you essentially are going to be going 30 degrees from that positive x-axis counterclockwise, and then have a modulus of 4. All right, let's try this next one. So we see that we're rotating around 7 pi over 4, so we can have these in radians. That's going to be in quadrant 4, and our modulus is root 2, so that's about 1.412. So I'm going to be really careful and revolve this around over here. And then I'm going to be going out, yes, a little bit more than one there. There we go. So that's going to be, if I put this in vector form, it's going to be a smaller one here. So this is going to be my 7 pi over 4. And this is going to have a length right here. of square root of 2. Now let's go back and convert it into a standard form. I'd have square root of 2 times cosine of 7 pi over 4 plus I sine of 7 pi over 4. So pi over 4 is my reference angle. I will get square root of 2 times cosine is going to give me 1 over root 2. It's like a 45, 45, 90 triangle. Plus, and sine is going to be negative 1 over root 2 pi, or 1 over root 2, times I. So when I multiply the root 2 through, those cancel, and I get 1 minus I for my standard form there. And that looks a lot like where I plotted that point right around here. Looks good. All right. In our last example here, I'm going to show you how to sketch the number in regular form, and then we're going to convert it over to trig form. So I have negative 8i. That is going to be right over here. So 0 in the real axis and down 8. So this would be the vector that looks like my negative 8i here in standard form. So now what I want to do is I want to find the modulus and I want to find that angle. The modulus is pretty easy because we don't really have a triangle here. We know that it's going to be 8 units away from the origin there. If we look at the angle, this is one of those quadrantal angles, and we know that since the point 0, negative 8 is there, this is going to be 270 degrees. So this one's pretty easy to write in trig form. It's going to be 8 times the cosine of 270 degrees plus I sine 270 degrees. And that will give us the same value as negative 8i. This next one we want to plot first in standard form and then convert it over to trig form. So in the next section, you'll be working with these a little bit more. So again, I want to know what 2 root 3 is. We said earlier it was 3.46 approximately. So I'm going to go over to the right, 3.46, and then I'm going to go down 3. So I'm right about there. And that is going to be where my W2 is. It's going to be 2 root 3 and negative 2i. So now what I need to find is I need to find the angle here, theta, and I need to find the modulus r. This actually is going to be one of those nice triangles. So I know that if I go over 2 root 3, and if I go down 2, that this is actually in a ratio of 1 times 2 and root 3 times 2. So the r would be the small side negative 2 times 2. Of course, r always has to be positive, so r is going to be 4. And since this is a 1 to root 3 to 2 triangle, we know that this is going to be a 30, 60, 90 triangle. This angle here, reference angle, is 30 degrees because it's across from the smaller side. So we know theta is going to be 360 minus that. So that fairly easily, if we know our triangles, becomes 4 times the cis of 330. Now let's say that we didn't see that that was a nice triangle like this. We could always get it a different way. So if we wanted to, we could let r equal the square root of each of these squared. So 2 root 3 squared plus negative 2 squared. So 2 squared is 4, root 3 squared is 3, and 4 times 3 is 12. Negative 2 squared is 4. So we have square root of 16, which is 4. That's verified from what we had over here. Same thing. So the modulus is still 4. Now, if we want to find theta, we can find a reference angle by using inverse tangent. So I'm going to use inverse tangent of opposite over adjacent. That's negative 2 over 2 root 3. I'm going to throw this into degree mode. My in there. So if I do second tangent of negative 2 over 2 second square root of 3, make sure I put that in parentheses. It gives me negative 30 degrees. So what that's telling me is that since inverse tangent is only going to give us an answer in quadrant 4 and 1, and if it gives us something in quadrant 4, it's going to be negative, that tells me that the reference angle here is going to be 30. That's the angle from where we're terminating to the positive x-axis, the acute angle there. So I know that theta is going to be 360 degrees minus that 30. Or 330 degrees, which, is verified right here. All right. I hope this section in examples will help you go between trig form and standard form. In the next section, you'll see that if we can convert these complex numbers into trig form, we can actually work with them a lot easier. It's pretty neat. All right. Thank you.